On that lighter note, let's get back to Claisen condensations. Claisen condensations are different than aldol condensations because there is no addition product, and there's a different carbonyl that's required. What carbonyl do we use with Claisen condensation? Esters. So let's run our first example, which is what compound? What is the name here? Oh, wait.
This is going to be so fun on the final.
Okay, you want some options? Multiple choice?
Yeah.
Is it ethyl acetate, methyl ethanoate, ethyl formate, or ethanoic ethane?
That didn't help, to be honest. Sorry.
The second one. Sorry.
Okay. I'm going to just keep a running list. You guys can keep going. Let's have there's like 6 of you, so.
I'm sure ethyl acetate.
Ethyl acetate.
I'll go to the second one.
Second, methyl ethanoate.
I'm going to go ethyl formate.
Ethyl formate.
Methyl ethanoate.
Methyl ethanoate.
1 or 3, down for half on each.
Yeah, you'll. Okay, let's.
What?
Milena? Are you tied between 2? Because that would give me some even numbers to put in here. All right, I'll count that as a full vote here and half a vote on these. Okay, why should the 4.5 of you, why should you have been able to rule out methyl ethanoate straight away? There's a 2-carbon chain. Methyl is a 1-carbon chain, right? Nowhere in here is there a 1-carbon chain, so methyl should have been out. Does that seem like sound logic? You guys know that with multiple choice answers, there is a skill to it. You should be able to rule out all of the other options to feel confident about the one you have. What's your question?
Nothing, sorry. I think I know why mine's not. Because it's formate, because form is 1, right?
Form is the 1-carbon carbonyl. What other forms do you know?
I don't know, I just remember that that's just 1.
You do, the one that we pump into dead bodies. You know it.
Formaldehyde.
Formaldehyde is a 1-carbon carbonyl, and ethyl formate is a 1-carbon carbonyl. Yeah?
Yeah.
So form would have been the clue there. I was hoping to hear more of what Elliot had said, which is either 1 or 3. I know it's an ethyl chain, but that just tells me you're not familiar with the common nomenclature enough, right? Ethanoic ethane didn't seem to pull on any of you because that just is a silly name. Ethanoic is what we call an acid. So we could have had ethanoic acid, but ethanoic ethane. I gave that to you because it's a 2-carbon chain. It looks like if an ethane chain was substituted by carboxylic acid. That was me kind of hitting at, if you really don't understand the nomenclature, you might suspect it's this. So ethyl acetate. I think a lot of you might be familiar with acetic acid. You certainly are familiar with it in a real world sense. Acetic acid is vinegar. And acetic acid becomes acetate for its ester compounds. Okay, that was good. This is a compound that we're going to use a lot, so I do want you guys to be familiar with it. Okay, ethyl acetate. Does that mean you did not use ethyl acetate today in lab as a solvent?
I don't think so.
Oh. Or ethyl acetoacetate? Did you use that in lab today? No.
We just used ethanol.
Yeah, that makes sense. There's actually is it okay if I erase this?
Yeah.
There's a different lab. I think it's also a alpha carbon condensation reaction. But I took that one out of the procedures. But after seeing you guys leave 2 hours early today, it made me think, why have I not just combined those two procedures to have you do both condensation reactions in one lab period? You're lucky. You got out early. Okay, the product of Claisen condensation with esters. What functional group do we have here? Remember, this is one of those new functional groups we introduced at the beginning. Good. Beta-carbonyl, carbonyl. This case, one carbonyl is an ester, one is a ketone, so it's a beta-ketone ester, beta-keto ester. And the beta carbon, of course, is here. Here's my alpha. And guess what? The beta carbon was a carbonyl carbon. So if this is alpha, this will become a nucleophile, and it will substitute the ester linkage. It becomes a nucleophile, attacks the new beta carbon, and substitutes the ester linkage. We need a base to catalyze this reaction. This set of compounds can only works well with one base. What base do I need to introduce? Can I use hydroxide? Hydroxide will hydrolyze these esters. It will saponify them into carboxylates. It'll ruin it. What base can I use? Ethoxide. I need a base that matches my ester linkage. That way, if the base does attack the carbonyl instead of deprotonating the alpha carbon, then at least it gets kicked off and leaves me with the exact same ester. I'm not looking to trans-esterify, because if I end up with 50% ethyl ester product and 50% methyl ester product, it might be hard for me to actually purify my stuff in the end. All right, so that's our reaction. Do you want to see the mechanism again? We saw the mechanism last week, correct? Oh, do you know what I'm not putting? Oh, and I don't know that I got to pick a lane and stay consistent with this. I don't know that you'll see this on the practice exam, but we talked about with the mechanism last week, the product of this reaction is far more acidic than the starting materials. And if the starting material's alpha carbon was deprotonated, then the product's alpha carbon will be deprotonated. So technically, we should be putting over this arrow, first introduce a base, then run an aqueous workup to neutralize the product. you may, I think this is what I'm going to consistently say going forward, but you may find that on the practice material, I was not consistent with that. No, I was consistent with that. Okay. Good. Sorry. Elena?
So if we do the reaction like step one with an excess of the dark side, we would end up attacking the alpha position, or could that happen?
Here.
Yeah.
It's not even an excess. So this is a catalyst. It is regenerated by the reaction. But whatever amount you have provided will end up deprotonating this. Because this alpha position is more acidic than the ethanol. So this will deprotonate the final product and form ethanol. And ethanol is less of an acid, so it won't reprotonate it. Do you guys want to see the mechanism again, or do you want to just move on to more practice problems with it? Yeah? We'll look at the mechanism for this.
Can I ask one question that you probably already talked about?
Sure.
But so for the ethyl oxide, can that be? I know it can be methyl oxide. Can it be any alkane chain, or is it just methyl oxide and ethyl oxide?
Methyl and ethyl are definitely the most common, but it can be any carbon chain.
Okay. Does it have to be sp3 hybridized? I can't remember what I'm trying to think of. Does it have to be sp3 hybridized, or can it be like sp2 too?
Good question. If it is an sp2 hybridized alcohol or ethoxide, you're technically working with an enolate, which has different pKa's from your actual alcohols and are nucleophilic from here rather than here. So basic from here rather than here. I'm not going to give you examples of this that aren't methyl or ethyl, if that makes it any easier for you.
Yeah, that does.
But you could swap it and make a propyl chain, isopropyl, N-butyl, sec-butyl, tert-butyl. In theory, you could use any of those. All right, so starting off our mechanism, my base acts as a base. It deprotonates, and remember, there's two resonance forms. I'm just showing the major form. I'm not showing the reactive form. After I form my enolate, the enolate acts as a nucleophile. Alpha carbon attacks the carbonyl carbon. That's how my beta comes into existence. I forgot something, as I often do. Actually, a couple of things. So as you're copying things down, I'll fill these in. This reaction is a condensation reaction. What we have condensed out is an equivalence of ethanol. Remember I said that alpha is substituting the ester chain on beta? Well, that ester chain gets kicked off as a molecule of ethanol. In the first step of my reaction, I generate that ethanol. It becomes a byproduct right from that first step, which means I have not regenerated my catalyst. You should notice that in this second intermediate, I have simply done acyl addition. Although the carbon chain can feel quite strange, and I did abbreviate the ethyl ester chain as OET. After this acyl addition, the carbonyl reforms and kicks off that leaving group, ethoxide. And the reaction's done. I have my beta keto carbonyl, right? Lily? This one?
Like the one on the first step that we moved it so it would have like a negative charge?
This one. So negative charge becomes a carbonyl. Here's that carbonyl. And carbon attacks carbon, breaking the carbonyl open into a negative charge. And O to ethyl is O to ethyl. 1, 2, 3, 4 oxygens. 1, 2, 3, 4 oxygens.
Okay. But then in the start we have 5 oxygens.
I have ethoxide, yes.
Oh, I see, okay.
I forgot to show that when I ran through it the first time. So that is the condensation product forming. Okay, so is this the end of the mechanism? It is not, because again, our acidity has just increased by like a billion-fold. So that catalytic base that was helping this reaction proceed at first is now trapping my product in this enolate form. And to get my final product back, this last step will just be shown as the aqueous workup. We introduce some acid. And again, the reactive part, the nucleophilic part, the basic part is the alpha carbon. And by the way, if I don't run that acid workup, I'm actually in a great spot to do some alpha alkylation. I could introduce 1 bromoethane. Didn't have to say 1 there. There's no other option. I could introduce bromoethane. I could introduce, yeah, you get it. Remember we did alpha substitution before we started the aldol condensation reactions. And we said it is these beta keto carbonyls that do alpha alkylation really well because it's easy to deprotonate them and make them into the nucleophile that we want them to be. Elena.
So on that last step in which we have the alpha carbon attacking the acid, it is the alpha carbon that's doing that and say not the oxygen with the negative charge because of the natural reactivity of the esters because of the oxygens they're not there. So like what is it?
Why does the oxygen not become protonated instead of the carbon? Oxygen is more electronegative. So oxygen is happy to hold on to electrons. But remember, those electrons are not on oxygen. They are in an orbital that is split between oxygen and carbon. So oxygen is happy to hold them. Carbon is itching to share them. And so when something comes in that is an electron acceptor, a Lewis acid, whether that be actual Bronsted-Lowry acid or an electrophile, carbon is the better Lewis base. Oxygen is less likely to do anything with the electrons. Like that vocabulary?
Yeah.
Good vocab review, right? Right before the end. Oh, man, the end of all the organic stuff I can teach you. No, just kidding. We're just scratching the surface. Does that answer your question?
Yeah, the Lewis base makes it very clear.
Good.
It doesn't actually matter which way you do the, whatever the middle step, like you could attack either carbonyl, I guess.
Well, we would not attack this carbonyl on the left. We wouldn't attack this alpha hydrogen. We would only attack this. But you're right that I could have formed the enolate on this carbonyl or this. I'm also happy to allow you guys to show the carbon holding the negative charge because it is the carbon that will do the next step. So you'll remember back with the aromatic reactions, I was very adamant, show the major resonance form. But none of the resonance forms were really implying what was going to happen next. The resonance forms instead were explaining why we form the regio product that we do. It's ortho or para because it engages with resonance. Here, yeah, it is more acidic because it can form one of those two resonance forms, but I want it to be obvious to you guys that it attacks from the carbon, so you can show the negative charge on the carbon. I'm not, because I think the major resonance form is a better tool for us to use. Okay. Fun, right? Now, unlike Claisen, we have the Deichmann condensation, and I'll be honest, I always spell it wrong, so I'm going to guess that my E and I are backwards. Yeah, but can you trust that I spelt it right on there? And Deichmann condensations require diesters. I'm not sure if Claisen and Deichmann knew each other, but they were just killing the same bird with the same stone. The Deichmann condensation is an intramolecular Claisen condensation. That is all it is. Intramolecular Claisen. So you see that I've got this diester on your sheet. And I've got a slightly different ester linkage now, which means I need to use a base that matches it. Would anybody suggest the base that I need? Peyton? You can't smile that big and not expect me to call on you. Should I use ethoxide again?
Yes.
No, because I don't have an ethyl chain. I need a MEO minus. Yep, methoxide. Followed by that aqueous workup. All right.
Yes. No.
This is a symmetric Deichmann reaction. It doesn't matter where I name alpha and where I name beta. Either way, I'm going to get the same product. So let's say that this is alpha, which means this becomes beta. Can we agree with that? If the alpha of one carbonyl gets deprotonated, the beta of the other gets attacked. Or the... Oh, I did. I'm sorry. This is not the ester I have on your sheet, is it? Okay. Yes. Yes. So when you actually put it on yours, show it with ethoxide. Was that how you got confused? You can take the win for that, yeah.
Yay.
Do you agree with the analysis that if I claim alpha of one carbonyl, then beta will be the carbonyl of the other carbonyl? Because beta was what? Beta was a carbonyl carbon. All right, well, alpha attacks beta. That's 1, 2, 3, 4, 5, 6. I'm going to create a 6-membered ring through this process. Again, alpha has just attacked beta, and I now get my intramolecular Claisen reaction. I have a beta keto ester, but instead of having a linear beta keto ester, I also have a ring in my new product. Yeah? I've formed a ring through this reaction. Can we what? We actually, if you're gonna do the mechanism, it's this. If you're gonna do the mechanism, I would like you to do it on this next practice problem that's not on the worksheet. Are you guys good with this? Can I erase? I stopped asking at some point, and glad I remembered to start asking again.
Well, I mean, you do record it, so it's not that bad.
Yeah, have you ever gone back to take the pictures from the recording?
Take the pictures from the recording.
Oh, you just pull up the recording, right? Silly me.
I did take pictures.
Do you ever erase these pictures after you take them?
Yeah.
Good, good, good. I'm just curious.
Like,
I take pictures of stuff that I never look at again.
I used to. And I convinced myself that I'm gonna write it down too.
And then I pay Apple for the storage. All right, I want you guys to solve an asymmetric Dykman condensation problem. And this time I'm going to use a methyl ester. The difference, I've added a methyl carbon to one of the carbonyl positions. I've added a methyl carbon to one of the alpha carbon positions. And once again, we'll react this with a base that matches before we introduce an acid workup. Last time I said it doesn't matter which position you call alpha, the other carbonyl will become beta. These are symmetric, so it doesn't matter how it gets attacked. But now there is a difference. One carbon is more substituted than the other. So the product that you get at the end will have that methyl group at different places. One of them will leave the methyl group at this alpha position. One of them would leave the methyl group at this alpha position inside the ring. And what I want you to determine is which condensation product, which Dykman product, is the only one isolated. There are two possible ways that this asymmetric Dykman reaction can run, and only one product is ever picked up. So solve for those two products. If the mechanism helps you understand it, good. And think about how the mechanism could help you identify which product is not isolated. Let's take, shall we say, 8 minutes on this? 9. 9 minutes. We'll go until quarter after. They quit?
That's a break, actually.
It's not break. I'll give you a break. Sorry? Oh, talk to me. No, I'm just kidding.
He wants to be clear.
Did you get my feedback today on your Unit 1 homework submissions?
I resubmitted one just this morning.
Oh, I might have graded it immediately then. Good. Well, let's, after you look at it again, maybe we find a time this week or next week to look over it together.
Okay, thank you.
Yo, I got a question. So, could this carbon here act as the alpha carbon,
Absolutely.
even if there's a methyl coming on?
It has a hydrogen, right?
Right.
So
Yeah.
the hydrogen there can be deprotonated. I erased the mechanism from earlier, but it can be deprotonated, which means it can become a nucleophile. Absolutely.
Fair enough, yeah.
So like we said, there are two ways that it can go, but only one product that will be isolated. That was the ugliest plus sign I'd ever done. I couldn't stand it. Can you identify the two products, can you think about where in the mechanism they have differences and how that might lead to proving which one forms? I've never sat in these. Oh, wow, it's kind of low, huh?
Yeah, these are low.
Oh, but they move. No, it's fine. I did raise it though.
Wait, are there two equivalences of this?
No, unlike Claisen, we don't need two equivalences
Okay,
because the two esters are already present on the same molecule.
okay,
So you're off to a great start.
that's right.
This is how the first step would happen.
Okay.
And then think about what happens in step 2.
Oh.
That's one of your products, good.
Oh, does that mean they're gonna do the other one too?
Sure. But I also want you guys to leverage the mechanism to figure out which product
Yeah.
is isolated and which one is not.
This is the one I chose.
Yeah?
Yeah.
How come? Can I hear your reasoning?
Just because there's two hydrogens here, so the second deprotonation step, maybe is the second one. I don't know. That was my thought.
Sure. So after this one gets deprotonated and attacks and then forms the beta ketocarbonyl, there's nothing else for the base to deprotonate and lock it in. But here, it can deprotonate in that second step and lock it in as that carbonyl.
Yeah.
That's exactly right.
Sick.
But maybe show what the other one looks like and then circle the one that is formed. That's okay. So those are your two possible attacking positions.
So is this like a, I kind of missed the first 2 minutes. Is this like one was more likely to form, or is it just that they both can form?
They both can form. Well, they both can react, but then only one of them will actually form. And if you look at the original Deichmann condensation example, the only thing I'm modifying is the alpha might go, or the methyl group might go on the alpha that's currently labeled in the final product, or the alpha might go, the methyl might go on the alpha carbon to the right of the other carbonyl inside the ring. So there are two possible products. The mechanism can clue us in on why one of them forms. So I would say pick one side, show that alpha carbon getting deprotonated, acting as a nucleophile, essentially mimicking this mechanism, but for that product on the left. And that's after you get caught up. What are you thinking?
Like, I'm just gonna try to do the mechanism with it, but yeah, trying to see if like there's not gonna be any weird tech things or something.
No, there won't be anything weird like that.
Okay, so basically, from what you just said, it has to be at this location because there's only 2 alpha hydrogens in this, like, there's only 2 alpha hydrogens on this guy. This one only has 1, so you can't do the full
Mechanism.
Yeah.
Yeah.
Okay, but this one would be more acidic, right?
Yeah, that's fair.
'Cause that was
Absolutely.
My first thought, but
Now, your product predicted, though, has,
yeah, this is.
it's got the methyl in both.
Yeah, I was drawing this
Positions.
for maxes, so I didn't have to redraw the
I see.
This was for max.
Good.
Anyway, it would be, it just.
Happy birthday, Max. I'm just kidding.
Yeah,
So
my
it would
birthday was
just be that,
last week
right,
actually.
that-
So.
Really?
Yeah,
Oh, nice.
it was.
Happy belated birthday.
I think it was Tuesday last week. I think.
Oh, and you came?
I didn't
You-
come.
No, he wasn't.
Oh,
No. Yeah, I was in lab and I was like, I don't feel like going to class after 5 hours of school. I'm good.
yeah, I don't blame you.
And I had tacos, so I think it's worth it.
Nice.
So what's that?
It's 'cause, like, in this one, the example,
Once again, 2 things. Can you prove both products? And can you rationalize which one forms?
but in this case, we can't really replicate that because this alpha only has 1 hydrogen.
Hello.
Right? It has that like second step where it
Scared me. Caught me with my eyes closed.
do the first step, but it can't do
I'm stuck on the second step.
Make it so it's less
Like,
acidic.
I don't know what happened.
Yeah.
Oh, okay. Well,
For that reason,
deprotonation.
you would
Yes.
only have
What is
this
that?
one.
Acyl addition?
Oh, I can see why you're a little confused about this. This was O minus,
Okay.
not O ethyl.
Okay, that makes.
Yeah,
I was like, I don't get where this is coming from.
yeah.
Okay. So, because that's
you-
what we had just changed.
Yeah, yeah, yeah.
Okay.
Yeah, you just made that a minus shade. Yep.
Okay, that makes, and this is the second
Yeah.
equivalent.
So what is this? Correct. When I did this, I actually drew the second equivalence beneath it at the same time.
Okay.
So I kept both equivalences the whole way through.
Okay. That makes sense.
What could we call this step?
That's not acyl addition.
It is
Oh,
acyl
okay.
addition. Okay, show me acyl addition.
Oh, wait, so I'm just having a really hard time saying how this is forming like I know it does, but I'm having a really hard time like seeing it come together.
Yeah, yeah, yeah. If I could give like a visual analogy, I can create a ring with my body.
No.
I can.
Sorry.
If I link my arms together, a ring, right? I have taken two parts of my body that are not near each other physically, and I have joined them, and then everything that already connected them in the first place loops them back around. So the way I might number this is alpha, beta, 2, 3, 4, 5.
What's our
Or
byproduct?
ethanol or methanol. This,
Oh,
and,
like the
and,
same thing?
and alcohol condenses, yep. Alpha, beta, 3, 4, 5, 6. That's what I should have said. Do you see how, like, my shoulders right now are not a part of a ring, but if I take my hands and make a ring, now my shoulders are part of a ring. These are not part of a ring, but if I link alpha and beta, alpha, beta, 3, 4, 5, 6, now I do have a ring. Like that. That was the substitution. It's wiggly. So this, all of this actually goes through conformational rotation.
Oh, I'm seeing things. Yeah. Okay, wait, hold on. This is gonna leave, and then I literally just had to remember stereochemistry existed.
Yeah,
Crazy.
stereochemistry does exist.
Yeah.
We don't talk about it as much in OChem 2, do we?
No, but that would have been helpful for this one, honestly, for me.
Conformational rotations.
Yes.
Good. All intramolecular reactions depend on it. No, this is just a different conformation of the starting material. Peyton was saying she was confused about how this beta carbon got to move so much closer to the alpha carbon.
Oh, no, I'm confused now.
But it's just a specific conformation that's needed. All right, two possible products can form in this reaction. I'll color coordinate these. If this alpha attacks this as beta, alpha, beta carbonyl, here's my methyl group. Alpha still has a methyl group on it. In green, if this is my alpha and this is my beta, alpha, beta, off of beta is the other alpha position. These are my two possible products. there is a point in the mechanism where they differentiate from each other. Elliot brought up a good point, which is that the orange alpha position is more acidic. It's more substituted. So it should form a nucleophile, an enolate, more readily. If we work with that nucleophile, and we show that nucleophile perform acyl addition, we get our beta keto ester. And by the way, we are, oh no, I'm sorry. We get our acyl addition. I'm skipping the part where the base has deprotonated it and we get that equivalence of ethanol. After this, acyl addition, the carbonyl reforms, the leaving group is kicked off. Remember, the leaving group here is meant to regenerate my catalyst. So my leaving group becomes ethoxide. What did we say happens after that in the mechanism? It takes the other alpha hydrogen, the one that is 10 billion times more acidic than the starting material, and it locks it as this ion that can't do anything until we protonate it. Okay, where is that alpha hydrogen? Doesn't exist. The alpha hydrogen that is 10 billion times more acidic is gone. Now, what we didn't discuss in these steps is that each step along the way is in equilibrium. It's readily reversible, except for that final deprotonation step, because there's an acid-base difference of pKa of 11 versus pKa of 16, so a 10,000 times different pKa difference. I can't do that anymore, which means I now have two carbonyls that are vulnerable to acyl addition. And if I run acyl addition here, I end up setting myself backwards in my mechanism. And if I set myself up backwards in my mechanism, then I might not kick off ethoxide. I might end up kicking off what was my nucleophile. This is so much fun. Thank you for saying that. And because of originally, my ester is less acidic than my base, this reprotonation back to the diester is easy. I forgot my alpha methyl group. And this alpha methyl group. Did you say what? So yes, this alpha position is more acidic, but the process to the final product is entirely reversible. It isn't until we get the other structure. When this enolate forms, and the difference in their pKa's is maybe 1 order of magnitude, so a difference of 10 times the acidity. When this enolate forms, it runs acyl addition just as we suspected earlier. Can I skip a few steps? We get back to this Deichmann product, except this time I do still have a second acidic acid, and so my catalytic base now acts as a base. Once again, deprotonates. We call this a thermodynamic trap. This will not go backwards. It won't reprotonate the alcohol. This is not vulnerable to the acyl addition. So we could pull out a pattern, right? We could say asymmetric Deichmann reactions favor the nucleophilic attack from the carbon with more hydrogens. And we could call it Deichmann's rule. And we could make it sound like it's hydrogen's fault. Like Markovnikov's rule makes it sound like Markovnikov addition is the hydrogen's fault. In reality, it's not about the hydrogen, it's about the acidity. It's about being able to be trapped and wait for an acid workup. So do you see this issue? My nucleophile attacks, it gets to the product, but in the presence of the base, it just reverses itself. Nothing happens. Versus the other side, running to the product and then getting deprotonated, and it can't reverse. If we were to draw this as a reaction coordinate diagram, one of these looks like this. That's the orange one. It gets to that final product, and then it just reverses itself. But the one in green, the one that has that final deprotonation, looks very similar, but after it gets deprotonated, it falls into this energy well, and it can't go back up.
So that final product's in that box and it will finish with a negative charge?
No, because we do require this acid workup.
Oh, okay.
But at the end of step 1, we isolate this. So if I can redraw this, this is what we've just trapped by deprotonating that very acidic alpha hydrogen. It's lower in energy, so it's very hard to react with. Versus the other product we had that looks like the normal beta keto ester that we'd expect to find, but is easily reversed in this reaction. Is this a good visual of why red is not isolated because it's still too easy to react with, but green is isolated before the acid workup? Cool. Tell me.
On the shared alpha hydrogen on the last step, does it matter which side it?
No, there's 3 resonance forms here,
Okay.
and it does not matter.
Does it matter for any of the reactions that we do for the last step?
No, in fact, you're always welcome in these alpha carbon reactions. You're always welcome to show the negative charge on the alpha carbon. But I primarily show it on one or the other. But remember, if you're not showing the mechanism, and that's usually why you're doing this, if you're not showing the mechanism, you could show this resonance hybrid, which looks like a scary clown.
It kind of looks like a crab.
Everything becomes crabs. Crabs have convergently evolved how many times? Like 5 times? More than once. Ella and then Elliot.
Okay, I got stuck like really early on.
Sure.
So we picked you picked the hydrogen on the alpha carbon that was less substituted, right? Is that why we picked the one that was on the less?
Well, we did both.
Oh, darn it.
We looked at both possible products, and we said only this one forms. If you're trying to form this is the route that you take. This alpha carbon needs to become the nucleophile. So it gets deprotonated, it attacks the other carbon, it forms this. According to our mechanism, after you form this, you need to deprotonate the next alpha hydrogen. There is no other alpha hydrogen. So this reverses. It is still reactive to all of the reagents that are present.
There's not another alpha hydrogen because the methyl group is there, huh? Is that why?
Exactly. The methyl group is there, limiting the number of alpha hydrogens. So we're not able to run substitution from that position. And since it just reverses itself, the odds that we deprotonate the other one will inevitably happen, but at the end of forming the beta keto carbonyl, it is now far more acidic and it gets deprotonated and it cannot be reversed. It's now stuck as this product until we do the acid workup. So this is never recovered because as soon as it forms, it just doubles back and it reverses. So asymmetric Deichmann favors whichever intermediate can be deprotonated. That's the way to think about it. That's Deichmann's rule. Deichmann doesn't have a rule to my knowledge, but we can. I'm shitting on dead people all semester long, and now I'm naming things after them. Okay.
Does that mean that your alpha carbon has to have two hydrogens? Like, is that what we're saying?
No, we're not saying that it has to. I mean, for instance, if I had another methyl group here and it was symmetric, I wouldn't need to, because there would be only one Deichmann product I could get. It would be symmetric again. But
this is because it's asymmetric.
But the best product is the one that can get thermodynamically trapped. All right, the last thing on Claisen reactions, or Deichmann, I don't know, is if we're dealing with crossed Claisen reactions. Can you remind me what we meant by crossed aldol before we get into crossed Claisen? We said crossed aldol addition or crossed aldol condensation involved what?
You could make like 4 products, right, out of the 2 starting materials.
Instead of having one product because you've got 2 equivalences of the same thing, you've got combinations of products because you've got combinations of carbonyls. And we run into the same issue with Claisen condensation. If I want to run ethyl acetate and ethyl propanoate, and I react them with ethoxide, which carbon becomes the nucleophilic alpha carbon and which carbon becomes the electrophilic beta? There'd be a combination. And maybe there is a slight preference for whichever carbon is more acidic, but I could have ethyl propanoic react with itself. Notice how that looks a lot like our first product from ethyl acetate, but I've extended the carbon chain at both alpha positions. I could have ethyl propanoate being attacked by ethyl acetate. I could have ethyl acetate being attacked by ethyl propanoate. And I could have ethyl acetate being attacked by ethyl acetate. I want to try and point out these carbon chains. Here's propanoate. Here's propanoate. Acting as a nucleophile on propanoate, or on acetate. The carbon chains get a little messy, yeah? Definitely long. Counting your carbons becomes a very handy skill. Mapping your carbons, a very handy skill. Being able to label carbons in the starting material and map them to their places in the products. Map your carbons, count your carbons. But the crossed Claisen, it gives us all of the same problems that the crossed aldol introduced. So how can we get around crossed reactions? You have this. How do we get around crossed aldol? What was our best method for controlling the product that we want to get? Yes, there was a weird reagent that we used or something. LDA. Instead of trying to limit alpha carbons, and instead of trying to promote selective reactivity, we will run complete enolization. Remember, the issue with this cross-Claisen deal is that both of these can become nucleophiles, and both of them can become electrophiles, and less than 1% of them becomes a nucleophile at any given time. So there's really a full range of combinations that I can get. So rather than waiting for 1% to turn into a nucleophile and then allowing the reaction to proceed, let's take whichever one we want to be the nucleophile, and let's just completely enolize it. So I have given you a cyclic ether, ester. I think what I screwed up here is that we really will need a third step to introduce the acid workup. First, we'll introduce LDA, which means that this alpha carbon and only this alpha carbon will become nucleophilic. And then we introduce whatever electrophile we want. So let's run this with methyl benzoate. In the presence of LDA, this becomes alpha. When it becomes alpha, it's truly in that enolate form. After I form that enolate, I introduce my beta. I don't know how that red dot got there on the ground. I think that's been there since they installed the carpet. And I get my nucleophilic attack. Beta keto ester. There, yeah, you're right. This ester linkage gets kicked off, which means that it becomes a good base to that alpha position and it deprotonates it, which is why I need that acid workup. So there is an equivalence of methanol, because once again, this is a condensation reaction. So I'm condensing a small molecule out of the structure. So the byproduct is methanol. Good catch. All right. I did not give you guys a break, so why don't we do a quick break, And then we're going to talk about ways to retrosynthesize all sorts of crossed addition and crossed condensation products. Let's take like 5 to 7 minutes. We'll come back at quarter after. Mm-hmm.
I'm so lost on this step of how this is becoming the ring. And I'm like counting my carbons, still trying to figure out how it's becoming a ring, and it's not clocking in my head. Because isn't it attaching to the 1 carbon?
Mm-hmm.
So why is it on the 2 carbon?
Oh, you're counting too many carbons for 1.
Oh, well, that's nice.
6 is attacking 1, not 7.
Okay.
You have not enough carbonyls either. Can we start over?
Yeah. Do you want me to just, is this step good?
Perfect, yeah,
Okay.
that step's perfect. This one actually, there's no arrows, it's this intermediate you need to fix.
Okay.
Um,
Because then I'm having too many O minuses.
what might help is drawing the reagent in the conformation that helps, but I'm confident we can make this work. So first of all, would you agree that this is going to reform the ester?
Yes.
Okay, let's start by drawing that,
Okay.
the new ester, or the reformed ester.
Isn't that one just attached to the ring?
Let's not worry about the ring.
Okay. Just draw an ester?
Yep,
Okay.
that's an ether.
Right.
No, don't erase anything. The ester is similar to an ether, but it has the CO double bond attached to it. Do you see how you're reforming that CO double bond?
Oh, yes.
Good.
Okay.
There's your ester. All right, now, off of this ester is the alpha carbon, so let's draw the alpha carbon. Good. This is done.
This guy.
Correct.
Okay.
This is done. There is nothing else that will change about this. The rest of the chemistry is from alpha all the way over to the carbonyl carbon.
Okay.
Alpha 6, 7, 8. Why am I counting up? Alpha 5, 4, 3, 2, 1.
Okay.
Alpha 5, 4, 3, 2, 1. Whatever you want to do, you're going to make a 6-membered ring off of this carbon. This carbon will be included in a 6-membered ring.
Okay.
Yeah, I think that is a 5-membered ring. I know you counted it, but there you go. 1, 2, 3, 4, 5, 6, right?
Yeah. And
'Kay.
then this guy will be here.
No, because
It'll be here.
because this was your carbon 6.
6, 5, 4, 3, 2.
Mm-hmm. Good.
Okay.
And then at 1, you got your acyl addition.
Okay. So that's.
The double bond broke.
Oh yeah.
Good. Perfect. Now, this is not the same geometry that I drew it in before, but this single bond, it has freedom of rotation, so it can rotate all the way around,
Okay.
like taking a, I don't know, I don't have a good example here. I'm just thinking back to OChem 1, where we do conformational changes with like Newman projections. If I rotate this, I could have drawn these at this position
Okay.
at the top, and that's how I drew it for you guys. but it's all the same.
Okay.
Although if you do rotate it, these are here and this is here, but it's all the same. Now you've got it. You reformed your ester by doing acyl addition. You had not changed this.
Okay, which I needed to.
Right, you had the
drew
arrow.
that, okay.
Exactly, you had the arrows to indicate that you were changing it.
Okay, so that we still have this other alpha hydrogen here.
But we're not going to deprotonate it yet
Okay.
because I don't have a beta keto carbonyl yet.
Okay.
I still need to reform my carbonyl and kick off the ester leaving group.
Okay. Thank you.
You're welcome.
I love Facebook too, because people really just be saying whatever on there. They're like, my granddaughter came out as trans, and I don't know how to
Literally on Facebook.
save my life. I'm like, wow, Cindy, that's crazy. Thank you.
I like how it's attached to my email, so I'll just get an email that's like, this person commented this. This person's post. I'm like, cool.
I get texts.
Oh, that's so funny.
I was trying to do something. No, I started with this.
Yeah. Yeah, I mean, what is carbon 1?
Like the primary one. You know, there's like the, sorry, my hearing was like half falling out.
No, it's okay. Well, I would argue the carbonyl carbon is the primary carbon. That is the carbon of the highest priority functional group. And the alpha is adjacent to the carbonyl carbon. I think it's a little silly that we didn't name the carbonyl carbon. And by we, I mean chemists, organic chemists. It just has the name carbonyl carbon, but it has no other name.
So I was looking at, like the alpha carbon, like it's like next to like two different groups. So like it would make sense that the carbon would always be the primary.
Yeah, so I see what you mean. And the fact that the alpha carbon is in the product is adjacent to two different groups it defines why we have the beta keto carbonyl. Because alpha lies between carbonyl carbon and beta carbon. And the product is a beta keto ester, which means, by definition, alpha falls between ester carbon and the ketone carbon.
Okay.
Right? Alpha is always adjacent to carbonyl and beta, and the product is a beta keto carbonyl. So alpha is going to fall right between them. That's what you're doing, is recognizing the pattern, which is great. Whether it's the primary carbon or not, no, I don't know that I'd say that. But alpha will always be smushed between two carbonyl carbons.
I just had a question. If I wanted to like orient this separately, because like in my brain it looks different, can I?
You can orient it differently, for sure.
Like, well, okay, so like for the last one that we just did, like if I wanted to put like the carbonyl group like here and the methyl here,
Yep,
that's fine.
absolutely.
Okay, cool. Because it's like in the beta position, it doesn't matter.
Yes, as long as the structure is correct, it actually doesn't matter. This crossed aldol product that I drew can be drawn like that. I'm not sure why anyone would want to. But that is exactly the same as what you asked, which is all I'm doing is rotating around a sigma bond. And all of those rotations are legal. Absolutely. Okay. Let's talk about retrosynthesis. So far we've introduced the aldol reaction. Aldol addition is a ketone and or aldehyde gets deprotonated, the alpha carbon attacks the carbonyl carbon of another carbon. And we can do that with crossed reagents. But why can't I take an aldehyde or ketone and turn it into a nucleophile and then react it with an ester? Why am I only allowed to turn an aldehyde or ketone into an enolate before I attack another aldehyde or ketone? And the answer is, that's not true. So, to the best of my knowledge, these types of cross reactions weren't named at all, and they're not well distinguished. So, I will try to refer to them as simply crossed reactions, because I don't want to call them aldol, because in your brain that requires aldehydes and ketones. It should. I don't want to call it Claisen because that should mean esters. So these are just going to be called crossed reactions. Now, rather than introducing to you crossed reactions, I want to do this in the context of retrosynthesis. So, some retrosynthesis tips. Label alpha and beta. Those of you that through this unit have looked at these products and said, the functional group is a ketone. No, the functional group is a beta hydroxy ketone. The functional group is an aldehyde. No, the functional group is an alpha beta unsaturated aldehyde. This means that you need to take a bigger picture. You need to be looking for groups that are in the beta positions. 2, separate alpha and beta. These reactions all depend on alpha being a nucleophile and beta being the electrophile. All of these reactions are ones that form a bond between alpha and beta. So in retrosynthesizing them, break that bond. Sometimes the easiest way to do that is redraw the product, exaggerate the alpha-beta bond, and then erase it. And now you have your two components. And then 3. Can you guess what I'm going to...
Map your carbons.
Actually, this is kind of mapping, but good point. This is different than my normal retrosynthesis skills. No, normally I'm giving you synthesis tips, which would be brainstorm, map your carbons, work forward and backwards. This is a little bit different. It's very specific to these addition and condensation reactions. What do you think my third tip might be? As you're working backwards from these condensation reactions. Make sure you make beta a carbonyl carbon. Because regardless what reaction here you're retrosynthesizing, beta started as a carbonyl carbon. I will do one of the reactions that I've listed for you, and then I will have you guys solve the others. So collaborate with your friends. I don't know why I said it like that. Collaborate with your neighbors and decide which one you'd like to see, top, middle, or bottom. Which one would you like to synthesize? Retrosynthesize.
I like the bottom.
What?
I said I feel like that was like you like asking the question of like, are we friends?
I'm not consulting with you,
Friends?
but I'm not collaborating.
Why
No,
not?
my brain just freezes sometimes. I swear it's nothing personal.
Did you say that the functional group will always be the beta? So this, how did you say that?
The beta carbon of your product will always have started as a carbonyl carbon.
No, I was from number 1. You were like,
Label alpha and beta.
and then someone was saying like, oh, but that's gonna make an aldehyde. Oh, but that's gonna make a ketone.
Right, right. So remember the types of functional groups we've made in this unit. We've made beta hydroxy carbonyls, alpha beta unsaturated carbonyls, and beta carbonyl carbonyls. In each of those cases, that beta group is often overlooked. People will look at a beta hydroxy carbonyl and say, that's a ketone. No, it's a beta hydroxy ketone, which is evidence of an aldol addition. They'll say, that's an aldehyde. No, it's a conjugated aldehyde, which is evidence of a aldol condensation. So what I was saying here was take a bigger picture. Don't just look at aldehyde ketone, look at what's happening at the beta position. That will be crucial for you.
Oh, because then that gives you an idea of what the original function was.
Correct. Correct. Well, it helps give you evidence of it helps you plan how to retrosynthesize. All right, which ones would you guys like to see together? Top?
Bottom. The very bottom. Very bottom.
Bottom. I've got 3 bottom, 3, 4 bottom. Others? Max?
I'll be bottom.
You want bottom as well? Okay. Any others? Is that a majority? Okay. All right. What functional group do you see in the bottom product? Give me more. How are you going to map beta and alpha and beta if all you have is an ester? I should have taken my sheet up with me. I have an ester, correct. Can you give me more? There is an alkene. Can you relate them? Remember, there's like 4 groups here. This is an alpha beta unsaturated carbonyl. This is an alpha beta unsaturated ester. This is a conjugated ester. What type of, Lily?
Wait, sorry, are we going back to the cross reaction?
Sorry.
Or is this a cross reaction?
Yes, but we're doing, I forgot that I put that up there. I apologize. We're doing cross reactions in the context of retrosynthesizing them. Okay, so let me say this. We did aldol addition, and this gave us beta hydroxy carbonyl. We did aldol condensation, and that gave us conjugated carbonyl. And we did Claisen condensation, and that gave us beta keto ester. Aldol, we said, was exclusive to aldehydes and ketones. Claisen, we said, was exclusive to esters. But why can I not introduce an ester and an aldehyde, or a ketone and an ester? And so the big umbrella of crossed can be done with any combination aldehyde and ketone. So these beta hydroxy carbonyls, they were always beta hydroxy aldehydes or beta hydroxy ketones, alpha beta unsaturated aldehydes or alpha beta unsaturated ketones. This is an alpha beta unsaturated ester, which means that it was not strictly aldehydes and ketones. It's not an aldol condensation, although aldol condensation is the only way that we have seen to make a conjugated carbonyl. It's not aldol condensation simply because, to the best of my knowledge, they limit aldol to being reactions with aldehydes and ketones. So now we're crossing them a bit. I can get a conjugated ester, which means I'm not just working with aldehydes or ketones. I'm going to need an ester involved here at some point. But it's not Claisen, because Claisen gives me beta keto esters, and this is not a beta keto ester, right? And then how we're going to retrosynthesize it. Okay, step 1, label alpha and beta. Here's my carbonyl, and it's my primary carbon. Alpha off of it, beta. There's more than one beta position, would you agree? But the beta position of interest is the one that is double bonded to my alpha, creating that conjugated system. As I retrosynthesize this, by the way, I don't talk about this a lot, but a retrosynthesis arrow is often shown as this big arrow, this wide arrow. But I think the way that I've given it to you is like we're forming this. But we can say this is made from, I'm going to separate alpha and beta. So as I redraw my structure, here's alpha, here's beta. Step 2, done.
Where's that other carbon on the left?
On the right?
Yeah, right there.
Good point. Thank you. Lost a carbon in my chain. Lily?
That beta, why is that beta? Is that a beta? There's two betas?
Beta comes after alpha.
Okay,
This beta is not interesting.
okay.
It's not a hydroxyl group. It's not a carbonyl. It's not an alkene. This is part of a functional group. This beta is.
Okay,
So I'm following the beta of interest,
okay.
a beta that has one of my predicted functional groups. Would you guys agree I'm done with step B? No? Elliot? Sorry, step 2. I don't know why I called it B. Okay. And then the only thing left is step 3. Make sure that beta is a carbonyl carbon. Is it a carbonyl carbon? How about now? Great. That's it. I've now retrosynthesized these reagents.
How would that react together? Like, 'cause you have to kick off one of the oxygens.
Good question. Now, in this retrosynthesis, I'm not asking you to figure out how to show it forward, but let's do it. First of all, which of these reagents, the ester or the ketone, needs to become the nucleophile in order to form my product? How do you know?
Because it has the alpha carbon that has the 2 hydrogens in it.
And the alpha carbon always is the nucleophile. So if I want my ester to become the nucleophile, and I don't want my ester to react with itself, I don't want it to do a Claisen reaction, then I can leverage complete enolization. I'll take ethyl butanoate, and I'll first react with aldehyde. Do you guys want to see it as a full sequential list, or do you want to see each product that forms, or both? Both. What did you say? Okay. Well, I can do the list. Having the list will do both. If I react this with aldehyde, this is no longer an ester. It becomes 100% enolate. And now I can introduce my carbonyl. And this carbonyl behaves differently than an ester. It behaves as a ketone. And just like we had crossed Claisen reactions, this now can continue it will first do addition. It will give me a beta hydroxy ester, and then it will do condensation. Although to speed this up, you likely would want to add hydroxide with this reagent or after this reagent. That will drive the condensation product. I think if I were writing lab instructions for this, which is not an experiment I've ever done, I probably would say wait a short while and then run it. But this reagent itself can't react with hydroxide. If I had a reagent that could do aldol condensation with itself in the presence of hydroxide, I would wait to add the hydroxide later. So Jackie, that's what the list looks like. And then you get the final product. Now I'm going to draw the intermediates that form along the way. After LDA, I form my enolate. After adding in my carbonyl, in this case, I run acyl addition, but I have no conjugate acid to help me protonate this to make a beta hydroxy carbonyl. So I'm kind of stuck here, which is why after adding water and base, I can protonate this and then run aldol condensation, or what seems like aldol condensation. The rest of the time is yours to retrosynthesize the remaining two products. The middle one has more than one right answer. I think. No, I think I'm wrong. They all have just one right answer. Leverage complete enolization. Oh, I mean, you don't have to do that bottom part. All you need to do is show me the starting materials that get you there.
For this bottom one, you're just condensing water, right?
Yeah, water condenses out of it. So can we say this is an aldol condensation? Not really, because it has an ester in it, so that makes it crossed. Similarly, if I made an ester with a beta hydroxy group, that now is crossed. If I make a beta keto ketone, a beta carbonyl, and one of them isn't an ester, that's technically not Claisen. That's technically a crossed reaction. All you have to do is this part. Break them apart. And if we have time, there's one last synthesis that I'd like to do. Maybe I'll put it up on the board so that you guys can think about it as you finish these up. Thursday's class, we're doing our last reactions, Michael addition and Robinson annulation. And I'm going to plan for us to do some synthesis problems as well. This unit. We learned about LDA in this unit. We learned about it after substitution reactions. We learned about it on this worksheet where we have 1, 2, 3, how to control cross reactions. That's where we introduced LDA. This is the other retrosynthesis I'd like you guys to try and solve if you can. Tell me.
So for the first one, the alpha carbon could be either on the hydroxy or it could be on the carbonyl. Which one would be?
So carbonyl takes priority over alcohols.
Okay.
And the alpha won't be on the carbonyl, right? It'll
Right.
be off of the carbonyl.
Mm-hmm.
Good.
Yeah, yeah.
So it'd be like these guys. Right, that's
Sorry, I didn't know the answer off the top of my head. Yeah, that's great.
Okay.
okay.
Exactly right.
Cool.
So if the alpha carbon favors the carbonyl, right? Does that mean beta has to be the hydroxide carbon?
Good. Exactly. Which agrees with one of our functional groups, James. That top one on the right, that functional group is a beta hydroxy carbonyl.
I have like two short questions. For the first one, is that correct?
Yes, perfect.
And then for the second one, I was confused. So if this is like, that would be the alpha carbon, right?
That can be the alpha carbon. Actually, yeah, that would be the
Beta
best.
carbon, which would be that, right?
That can be a beta carbon, but it's not an interesting beta carbon. You're right that there can be more than one beta. Like here, also a beta carbon, but it's not part of a functional group. It's not a beta hydroxyl. It's not a conjugated beta. It's not a beta carbonyl. So you will be looking for the beta carbon that has some functionality going on with it.
So then, would you be like, because if that's alpha, then are you trying to say that beta would, like, does it matter then which one of these beta would be? Like, would it
You're
lean
right.
towards this one because it's the methyl group?
You'd have to decide. That would be up to you.
That one, like, there's no priority determinant?
Correct.
Okay.
You've got a beta keto ketone. Alpha definitely falls between them, but which ketone would be the beta?
Would be easier.
Maybe. I will say one of them is super plausible to make. The other is not as easy to make. So if you can even predict both versions, you'd probably realize then which one is harder to make. And by harder, I mean literally like solving it is harder. Which also means if you get stuck, maybe try going the other way. How you doing? Oh, you know what? Milena has just reminded me you can do it either way. Yep. There are two. I changed my mind on this enough. The middle has two solutions. Okay, I'll say this. The middle has two solutions. One is a crossed Claisen reaction. One is a Deichmann reaction. Kind of like a weird version of a Deichmann reaction. Yep, exactly that. Good. Up here? You have accidentally taken alpha away from the carbonyl. And actually, you've doubled alpha. Yeah?
Yeah, okay, I see, yep. So, alpha,
Beautiful.
and then that just leaves.
Benzaldehyde.
Yeah, okay, yeah, now,
Perfect. So you labeled alpha beta. You separated them. And then step 3 is make sure that it is a carbonyl, right?
Yeah.
But what type of carbonyl will go through these reactions and still leave me with a carbonyl? What type of carbonyl leaves me with a carbonyl?
When did we go over that piece specifically?
Oh, this morning. I mean, today at the start of class.
Awesome. That's why I'm confused.
So this type of reaction takes two versions of this ester.
I know it reacts with itself, right?
One stays as an ester, the other equivalence just becomes a ketone. Here, I've got a ketone.
So would you need that to be an ester?
Perfect. And if you flip this, either way to get two ketones, one of them will have to start as an ester.
If you were to do this as the cross Claisen, how do you know which one of these started as the ester?
You can do both. There's two solutions to it.
You said one was a Deichmann.
One is intramolecular Deichmann. Remember, that's the only distinction on Deichmann.
That's just an intramolecular 2-ester.
Right, but this won't technically be Deichmann because it won't be two esters.
Oh, okay.
Because it's one of our crossed,
Okay.
and it doesn't have a good name.
But like, if we wanted to do two separate molecules,
Mm-hmm.
one
There's,
would need to be an ester,
yeah,
and then one wouldn't.
and that is true for both syntheses. Both solutions require one group to be an ester.
Right. So how do you know which of the starting carbonyls was an ester carbonyl?
I think you'll figure it out when you get to step 3. Because with this product, after you separate alpha and beta, beta still is a carbonyl carbon. So it can't stay an aldehyde because aldehydes would react to do addition or condensation to the alkene, the conjugated carbonyl. So separating them and already having a carbonyl tells you it must have started as an ester and lost its ester linkage.
Okay, I'm gonna draw it out. I want to see that out.
Okay.
I don't know.
Well, don't label the carbonyl carbon as alpha. The carbonyl carbon, unfortunately, has no name, just carbonyl carbon.
But for the second one,
Alpha comes off of the carbonyl carbon. So this is alpha. I guess that would be the same mistake up here. But this is correct. You nailed this.
even with labeling my things wrong?
Well, beta was a carbonyl carbon.
But then this one is saying it is again.
What do you mean? Oh, yeah. Well, isn't that also true of the Claisen condensation? Beta stays a carbonyl carbon. Beta was an ester. Beta becomes a ketone. Yeah, you see that you've labeled multiple betas. Alpha, beta, beta.
Yeah, see, that's
Do you know your ABBs?
no. Because wait, on this
No,
one,
did you get
I
the-
label this wrong?
Did you get the joke, though? Yes, you did. Did you get the joke? Like your ABBs? ABCs? Because it goes alpha, beta, gamma in the Greek alphabet, not alpha, beta, beta. We are literally just using the alphabet to map the carbons.
So I drew this wrong.
You did, yes. This.
Okay, that's why I was confused.
Well, can't you see that it's wrong? You can't see from that far
I
away?
can't see the orange.
Oh, I'm sorry.
No, it's just me, I think.
No, you're not alone. I've had people tell me that in the past, but I thought that if I kept it fresh, it stayed easier to see. And this is just a dot, because I have no letter for it. It's a reference point. That's a good point. Did you solve this one? Did you solve these? That's fair.
Girl's confused.
This is good. Perfect. This works. This works great. Don't read into the way that I paused. This is great. This is one of the ways that you can solve it.
Yeah, I heard you say. I don't know the other way.
Is this
Well, it's
the
just
other way?
swapping which one you label as beta.
Alpha?
Yes, but you have too many carbons. Like alpha here.
So this
is still
does
here.
have to be okay, because that's what I was thinking. But then
This is a reference
like this.
point. We're using
Okay.
this one is beta.
But I know that I thought that was how like.
But
the
that
Deichmann
alpha
works.
is still there. It needs to be a group that can leave. It needs to be attacked. It needs to be attacked by this group and then have a group that it can kick off. Like when we did the Claisen condensation, ester had a group that could kick off.
I get it.
To form a beta keto carbonyl an ester must be involved at some point.
Two questions. So is this what the other variable would be?
Close. So this one's right. This one, if anything, like this alpha position might be able to come over and attack here,
Wait, what?
but this whole chain would be lost. Actually, what we need is for this chain to stay connected while this carbon here attacks that carbon.
So would you just disconnect that piece? Because this is.
Maybe there's 3 solutions to this. No, there's not 3. So remember we said alpha beta, label alpha beta, and then cut alpha beta.
ESO is intramolecular?
Mm-hmm.
So wouldn't it be connected?
They do have to be connected, but notice how when you cut alpha beta here, I'm going to do this on the board so I can make it big, okay? All right, so let's solve that middle problem. Like this. One solution where I reference this as my carbonyl and this ketone on the right as beta. Step 1 says cut alpha and beta. I have just cut alpha and beta. But I've made beta into an aldehyde. And when aldehydes get attacked, they can give beta hydroxy or alpha beta unsaturated. When aldehydes are attacked, they do not give beta keto. In order to get a beta keto group, I need to have a leaving group. The Claisen condensation showed us when the electrophile has a leaving group, like the ester, that group leaves and it results in a carbonyl staying. So when I see a carbonyl, an ester must have been in the precursor somewhere. Step 3 is make beta a carbonyl. It already is. So what else do I need to modify about it? In this case, I need to make it an ester. Now that looks a little funky, the way that it's all kind of squished in there, but we could count our carbon chain and we could draw it out as a long chain. This is intramolecular. It's all attached. It's all one sequence. So it's similar to the Dykman condensation, except that it's not 2 esters. Dykman requires that it's 2 esters. The other way that I can cleave this is to swap my alpha and beta positions. This actually becomes even easier to redraw, because now I don't have to draw this one long chain. But again, beta already is a carbonyl. How can step 3 qualify if beta is already a carbonyl? Make it an ester so that when it gets attacked, it has a leaving group that can leave.
Oh, it wouldn't matter. You could do it ONE or O. It could be an ethyl or like it could keep going, right? Because it'll just leave anyway.
Correct. Here it doesn't matter what the ester linkage is. I'm not having 2 esters react. I'm having just one ester and a ketone. And I'm going to use LDA to make my ketone into a nucleophile. And when it attacks the ester, it kicks that group off. Fun, right? Okay, thank you guys for your time. We can answer any remaining questions about this on Thursday. And then we dive into our last 2 reactions and synthesis. Yeah. Okay, yeah, let me close this. Have a good night.